Hey guys, welcome to another Back to Basics video that we're going to be doing. Got the old iPad scratch pad out here, so we'll be checking it out. Alright, let me make sure I get my microphone set up properly. Hopefully I'm not too loud. Okay, op amps. So, op amps. Okay, very useful tools. This is basically when you're playing around in the analog world. So far we've been doing mostly digital stuff, but since I'm going to be doing videos on more all hardware stuff, we probably should look at these little guys. This is a great way to do, at least that I've used them for, definitely in more of a discrete fashion rather than using them for amplifiers and whatnot, is in the DC world, which is what we'll be looking at. We won't look at any AC signals just yet, but in the DC world, they can be a great help for amplifying stuff. So basically using basically like a multiplier, where you can multiply a voltage by a certain factor and get it to grow bigger or grow smaller. Also, you can use it to build summing amps, where you can actually have 2-3 different voltages and it will actually sum them and give you the output. And you can even weight the output, where you can multiply each sum by something, and I don't know, just a lot of cool different configurations. Very helpful when you're doing a lot of analog work. So if you need signals, if you're trying to build, like, say, an equation or something in circuitry, you can use op amps to do that. So one of the first ones that we're going to look at is we will look at the inverting configuration. So very simple, and I'm not going to go through the how to derive the formulas for this. We're just going to go through them. Just they are what they are. If you want to know more, then I'm sure you can go to classes or get some books or whatever to help you better understand where these equations and stuff are coming from. But for right now, we are just going to, I'm just going to give you guys the basic formulas that you will need to use with these. So here we go. So this is, I'll draw like this, plus, minus. This is our voltage out, okay, our V out. Then let's say we have some voltage source here, and this is our V in, okay, so VI. And this little resistor is going to be R1. This guy will be R2. All right, so this is your basic inverting op amp, excuse me. Reason it's inverting is because the input goes into the negative terminal of the op amp. Okay, now a cool thing about op amps, rule of thumb to remember, is that on their inputs, let me erase this. Ooh, I kind of erase some of my resistor here. That's okay. On the inputs, they're usually the current that's flowing in to your inputs or whatever is usually, now they say in an ideal sense it's zero. It isn't zero, but it's very, very close. It's darn small, because they design these op amps in such a way that they have what's called high input impedance. So basically the input has a very, 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 very high resistance to it. So it usually draws anywhere from microamps to nanoamps to maybe even picoamps, depending on the precision and the type and all that stuff of your op amp. Okay, you can get very low input impedances. Okay, so that's a good thing to note. What that will mean is basically a lot of times you can hang an output on, let's say, a resistor stack and not rob significant amount of current where it will skew your numbers. And I'll show you what I'm talking about later. So that's a very useful tip, is that they have high impedance, okay? Input impedance. Now, the relationship for this guy, for input to output, is if you want the V out, since it's an inverting op amp, it's going to be a negative, let's see, make sure I get this right. I'm going to look this up real fast. Just make sure. I always get these backwards. Okay, yeah, R2 over R1 times the voltage in. Okay? So that is our little equation for coming up with these guys. So if we had basically two 10K resistors for R1 and R2, it would be the same as 1. So basically it would invert the input. If both of these, if we said, hypothetically, if we said R1 is equal to R2, we put them both at like 10K, okay? And then this guy is 10K. Well, oh no, my page flipped. Okay, and then let's erase that and move it over. R2 is equal to 10K as well. Well, of course, when you come to here, 10 divided by 10 is 1, right? So you would have -1 times, so yeah, your V out would be -1 times your V in, right? So it basically will invert your output. And that's hence why they call it an inverting op-amp, okay? And then what's great is, depending on this resistor ratio right here, you can multiply it. You can actually add some gain to it, okay? And so what it will do is it'll make that negative number either bigger or smaller, depending on what values of R1 and R2. And it can be any combination you want. Now, I would suggest taking and looking at the specs of your op-amp, and if the type of, depending on your input impedance, depending on your output impedance, because there's an output impedance too. You can only draw so much current out of these guys. So they are limited on how much current you can draw out of them. You might want to definitely stay in the kilo-ohm regions so far as when choosing your R1 and R2 when choosing these guys, because you don't want to suck too much current out of the op-amp in the feedback loop, or you want to shove, you just don't want to, you don't want your currents to be anywhere close to, the operating currents of the IC, because otherwise it'll skew your results. You might have numbers acting wacky on you. So definitely stay in the high kind of kilo-ohm resistor range when you're choosing your resistors. But pretty much anything goes. I mean, you can pick whatever kind of gain you want within a certain bandwidth of this guy. Okay, so depending on the bandwidth of it, which is defined in the spec sheet, depending on that, you may, you can't do, like, for instance, you can't do like a gain of 1,000. That might not work because of bandwidth limitations of it. They'll be rated in so many, megahertz or whatever. And so you got to watch your limits, as well as they should have what's called voltage rails. They call them rails, but it's basically the power. You'll have a power and you'll have a ground that hangs off of this guy. Okay. So looking at it, let's go to the next page here real quick. So if we're still looking at our inverting input, you've got your VCC and you'll have ground. Now this, when you have VCC and ground, of course you got your inputs and your output. What this is called a single rail power supply. Okay, so you can put, like +5 volts, let's say, on it. And basically your output is bounded by the voltage rail. So this output, V out, can only be equal to 0 to 5 volts. Okay, so even if on the input we put a -2 volts as our input, and then let's say our gain is 1, so our gain equals 1. So basically our resistors are 10K and 10K, okay, on our feedback network. So if we had our feedback network here, and our input resistor and our ground here, like that, and this is V in, and then that one's V out. If our resistors, our two resistors, this guy and this guy, are the same, we'd have a gain of 1. So basically our V out would equal 2, right? So now, but let's say for some reason we change our gain up and we do excuse me, I'm sorry, my allergies are acting up, so I'm sneezing. And we do a gain of 5, let's say. let's say we make R2, so that would be R2 would equal, let's say 5K, okay, and R1 is a 1K. So that way, when we do the, this is equal to R2 over R1, when we do that ratio, we get 5. Well, if we take, and let's grab an eraser. If that's true, then our V out will equal a -5 times -2. It's actually equal to 10. However, because we're bounded by our rail, we call it going to its rail. It'll basically go to the maximum voltage that you have applied to its rail, which in this case is 5 volts. So even though the equation, the math says it should be 10 volts coming out, in reality, because we've only got 5 volts coming in, we can't go any higher than 5 volts. We actually rail the amplifier is what they call it. Okay? So remember that you got to work within the bounds of what kind of voltage you apply, and then depending on what kind of amplifier you choose, some have the ability to go up to 12 volts, or some even go to 30 volts. It just depends. You got to choose the op amp for your application. Okay. Now there is also, excuse me, there's also what's called dual rail, where you have a V plus rail. And you can have a V minus rail. Now you can get a whole host of things. Let's say you've got, let's say you've got maybe some equation of a line. Okay, let's say that's easy, and it has no offset. Okay, right? So you have a line that looks like this, right? And this is the standard y equals mx plus b, right? Slope-intercept form. Those of you that don't know, that's what that is. Okay? That equation describes this line right here. Now, since this line is passing through the origin, we can say that b doesn't exist. So this is basically m equal, well, it's not that it doesn't exist, it's 0, because there is no shift. The line isn't moved over that way. It's right through the origin. So we can say that it's just some multiplier times x is what makes up, this line right here. Okay. Well, since this line can go negative, it can go on that side, we would need a dual rail op amp, right? If we wanted to fully represent this line. Now, if we were just representing this piece of the line, okay, just the piece that shoots off this direction, and it's all positive, then we wouldn't need the dual rail supply. We'd need just a single one with the ground here instead of this negative V. But if we're wanting to represent the line going in both directions, okay, we need a dual rail power supply because it can go negative, because this X number can go negative. Okay, that's another one with the previous one. Since it's single rail, if this input voltage was a positive 2, that would make this positive. That would make this a negative 10. Well, it would rail at 0, right? Same way as the other way. If it's going to come out to be a negative 10, and I've got this situation right here, I've got only 0 to 5 volts. I can't go below 0 because I've got ground here. I can't go below ground. So I can't go to negative 10. However, if I have a dual rail power supply, and let's say I put, well, in that case, since it was negative 10, I'd have to do like negative 12 volts to positive 12 volts or something like that. If I did that, then I'd get my negative 10 out, because it can go down there because of this dual rail. Okay, so that's where those are handy. So anyway, guys, I think I'll probably stop here, just because I don't want these videos to get incredibly long, and plus I want to probably make a few of these because there's a whole lot of different configurations that you can have. But for right now, that is the inverting op amp. And yes, there is such thing as a non-inverting, which we will look at later. Okay, but for right now, that's the inverting op-amp. Okay, usually it's got some rails on it somewhere. So I was thinking about, we may look at these even in LT Spice, just so I can throw some numbers into it and show you what I'm talking about. So this is like this. That's a minus. This is a plus. This is V in, and you've got your V out. And this is the inverting. I'm sorry, my handwriting is horrible. Inverting op-amp configuration. Okay. Oh my gosh, that. I'm sorry. I'm not an artist, as you guys can tell. Of course, I don't think really any electronics engineer is one. R1, R2. Or wait, I think I just did that backwards. I did that backwards. Just a minute. Pretend I didn't do that. R1 and R2. And our equation for the output is negative R2 over R1 times the input. I am going to move that around. There's our equation. Okay. All right, guys. Well, that'll do it for this video. I'll be showing you guys some of the others. There's non-inverting, there's a summing, there's an integrator, there's a basically derivator where you can do derivatives and integrals. What's awesome about these is you can perform all kinds of mathematical operations that normally you would use software to do, right? You know, you can add two things together and subtract two things. Well, what's cool is you can do those same math operations, but using voltages instead of digital numbers. And and that was one thing I wanted to show you. I'm sorry, let's not end the video yet. Just one more quick thing about currents. When I told you about how you can do a resistor stack or whatever, let's say you have, I'll try to do this real quick. I don't want this video to be really long. Okay. So you have resistors like this. Okay. The thing is, you know, you've got a certain amount of current flowing through here. Okay. Let's say that it's pretty small. Let's say that it's, you know, in the order of microamps that's flowing through this resistor stack. You know, and you may have like, you know, 3.3 volts up here, and you have like, you know, 2.5 and maybe 1.7, you know, is what's coming off here, here, and here, right? Okay. Now, what you can do is you can snag onto this. Let's say that we need to perform some sort of math operation on this voltage right here. You could snag onto this, okay, with your whoops, hold on, let me make this look more realistic here. You can have a resistor in there. Oh, my resistors are horrible. This iPad's kind of interesting to write on with these stupid squishy pencils. Anyway, so you can snag an op amp. Ooh, let's see if I can get it squeezed in there. That is connected. Okay. What's great about the op amp is since this current right here that goes in, we'll call it IN. IN may be 2 nanoamps. Okay? Well, with 2 nanoamps, that's a whole order of magnitude smaller than microamps. That's not going to see because remember, they like to say that op amps, the input resistance or the input impedance is, or the input current to the op amp is 0. It's not 0. It's very, 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 very small. But if you're dealing with, let's say, you know, you've got a PIC microcontroller that's doing nanowatt, or you've got, you know, something that you're going to be doing with batteries or something to where, you know, you can't be, you can't be hogging, 500 milliamps. Because then, if you multiply it out and it's only a 500 milliamp hour battery, that battery's only going to last for an hour just running this chip. Okay, or the stack of resistors, whatever that may be, the representative, let's say, your circuitry. So you're going to want to squeeze your circuitry as small as you can, keep it in, something like microamps or something like that, to where your battery life is longer, right? When it's sitting there doing its thing, it lasts. So when you have it in microamps, if this op amp is in microamps, it's stealing microamps too, then your voltage, it has a tendency, because remember, you've got basically a resistor here, resistor here, as in your stack. That's what I drew. Well, you're coming here and grabbing like this, and there's your op amp and yada, 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 all that stuff. The thing is, you're going to grab some current this way, which means you're going to develop a voltage, here, and the current from this source is going to go like this, but it's also going to split and go this way to go with that, okay? Which you create you basically create a voltage divider, another voltage divider, okay? Because inside here, it basically goes through here and goes to ground. That's what it's going to do, okay? Since you grounded that input. Well, that will actually cause the voltage at this node right here, this voltage at this node will go down, okay? Because it's robbing current from it. You're going to have a voltage drop, right? So you may not want that. So if you need to preserve that voltage, let's say, is very important, you need to trigger something off of that. What did I say it was? It was like 2.5 volts or something. It needs to be 2.5 volts. The little problem is your op amp is robbing current, and it's making that voltage sink. That voltage is going to maybe, let's say, 2 volts. Well, when in actuality, it really needs to be 2.5. Well, now you're going to be off. You're going to have error in your calculation because of that. So that's why it's important to choose your op amp, and I like to choose them in order of magnitude less than what current is going through. We call this a totem pole stack because you're stacking the resistors on top of each other like a in series, like a totem pole. So your totem pole here is in the order of microamps. Well, you definitely want an op amp that is either in nanoamps, or if it has to be in microamps, you make sure that this is maybe like 100 microamps, and the leakage of this guy, or its input impedance, and the current that will be sunk by the input is like a microamp, or maybe 5 microamps or something. That way you've got a huge gap. You can basically rob some current from this totem pole stack and not affect your voltages, across your components. Okay? So that's a good rule of thumb to remember when you're choosing op amps, and if you're doing any type of kind of precision work where you need the voltages across these resistors in these certain points, or anywhere in your system, certain points in your system, you want those voltages to be preserved and maintained. You don't want to affect them when you hook on your basically measuring device here, because a lot of times that's what these op amps usually, in this type of a situation, you're usually measuring the voltage at this point, and based on that voltage you're doing something with it. Well, to be able to measure it, it's kind of like your meter. That's why meters, I don't know if you've noticed that, but voltmeters will come in different ohmages. They have different input impedances, because I've had that happen with a meter where you're trying to measure something that's in nanoamps and the meter is in mega ohms. Well, when you get down to nanoamps and stuff, a mega ohm it's not going to cut it. It's going to rob too much current from the circuit. You need something that's in giga ohms so that way it robs. What's gigas minus 9? So that'd be pico amps. It's robbing pico amps. No, that'd be nanoamps. Sorry, my bad. I can't do math right now. That'll be nanoamps. So if you've got like a microamp circuit or whatever, you see what I mean. That's what you got to look for. You got to look for stuff like that, and that's what is important when choosing your op amps, that you make sure you choose one that has the correct impedance, correct leakage stuff, depending on what you are doing. Okay, this was a big misnomer that I've seen lots of engineers struggle with. I even struggled with it. I'm not going to say it's other people. I struggled with it when I first got into all this analog stuff. because it's stuff that you're never really told. You're always told that, hey, these amplifiers, their internal impedance, this current here, this I input, is equal to 0. Well, no, it's not equal to 0. So you got to look at the data sheet and see what it is. I mean, these are real parts, and that's one thing I recommend everyone. You got to wrap your mind around that these are real parts. They're not these magical ideal components where they're 100% perfect in every way. No, they are real things. They have leakages, they have inductance, they have capacitance, they have resistance, they have all of that stuff. So you have to take it all into account because they're not perfect, and nothing in this world is perfect. I've come to realize that definitely with electronics. Stuff seems to be ideal, but it's not. And it depends. Like I said, if you're working in amps and you've got an op amp that its leakage is nanoamps, well then it might as well be an ideal op amp, because that is so far, the difference is so huge that it doesn't matter. The op amp, it's never going to see that op amp. So that's what you have to keep in perspective. Keep your mind in that realm that what am I working in? And if I'm working in microamps and it's operating in microamps, there could be a potential problem. So look at it, okay? All right, guys, I've rambled on enough. Hopefully this video wasn't too long. I was trying to make it short. We'll look at some other configurations later on. Till then, like, subscribe, share, all that fun stuff. Check me out on Instructables if you haven't. I post stuff there here and there, as well as check me out on Twitter. I'd love to have as many subscribers as I have here, at least all of you that are subscribed. I'd love to have you on Twitter, not because I want to grow my Twitter page. It's just because I'll post things. I may tell you when a video is coming up or getting ready to come out and things like that, and that way you can stay in tune with me, because I can't always sit down and make an update video and tell you guys what's going on. I just don't have the time or whatnot to pull one of those off. So I'll give you kind of some updates via Twitter. I'm trying to use Google Plus more. Whatever I post on Twitter, I try to post on Google Plus, because I see that there's more of you on Google Plus with me than there is on Twitter. But either way, either place, I'll try to copy the posts to both of them, so that way if you don't want to subscribe to Twitter or whatever, you can get me on Google Plus, because I know how you have to have Google Plus to be on YouTube anyway, so I get that more people will be following me on Google Plus than Twitter. But still, either way you want to work it, that's where I'm at. You can get a hold of me on both of them. So anyway, guys, talk to you later. Like, subscribe, share, all that fun stuff. Take care. And that ought to do it.